Okay, guys, we are going to go through the chapter 5, section 5.2 notes now. Okay, we're going to talk about Bohr's model of the atom. Bohr correctly predicted the frequency lines in hydrogen atom's emission spectrum. The lowest allowable ground energy state of an atom is called its ground state. And when an atom gains energy, it is in what's called an excited state. So what Bohr suggested is that an electron moves around the nucleus only in certain allowed circular orbits. So you can see, whoops, sorry about that. So you can see here that we have electron out here in what's considered its ground state. The nucleus is right here. So these are lower energy levels. As you get out further, the energy levels start to increase. This would be the same atom in what's called the excited state. So the electron jumped from right here to out here to a higher energy level. So in this model, each orbit is given a number, and it's called the quantum number. So you can see right here, quantum number n equals 1, n equals 2, n equals 3, and so on. That is going further and further and further from the nucleus. So the first energy level would be closest to the nucleus. Second energy level would be a little further away. Third energy level, a little further away. So to kind of show you that, we'd have, this is the nucleus of the atom right here. This would represent energy level 1, where electrons could reside, energy level 2, where some more electrons could reside, energy level 3, where more electrons could reside, and so on. So as we get further and further from the nucleus, the energy level, or quantum number as it's called, gets larger and larger. Hydrogen was used for this model because it only has a single electron. It is in what's called the n equals 1 orbit in the ground state. The n stands for the quantum number, and that's the energy level. So hydrogen's 1 electron is in the lowest energy level possible, which is energy level 1, which is closest to the nucleus. So electrons will occupy the lowest energy orbital first before moving on to higher energy orbitals. If you add energy, however, to this hydrogen atom, the electron is going to move to a higher energy level. So hydrogen's single electron would move from the first energy level to the second energy level. Now it's kind of showing you here some visible series and infrared series and where these electrons can travel. Again, energy of the hydrogen atom, level 1 would be the ground state, and as you go up to higher energy levels, the energy increases for that electron. So what Bohr's model does, it explains hydrogen spectral lines, but it didn't explain any other elements lines. So the behavior of electrons is still not fully understood. We don't really know exactly what's going on with them, but it is known that they do not move around the nucleus in circular orbits. So de Broglie, he came along in the late 1800s, early 1900s, and he hypothesized that particles, including electrons, could also have wave-like behaviors. And this figure illustrates that the electrons orbit the nucleus in whole number wavelengths. So electrons behave similarly to light. They travel as waves. And the de Broglie equation that he came up with, he predicts all these characteristics of these moving wave particles around the nucleus. Again, we're not going to focus on this equation here, but you're not going to have to do any calculations with it. But again, this symbol represents wavelength. H is Planck's constant, so that's coming into play here. M is representing the mass of the particle, and V is representing the velocity. I'm sorry, not velocity, the frequency. Um, then Heisenberg came along and he showed that it's impossible to take any measurement of an object without disturbing it. So this uncertainty principle states that it's fundamentally impossible to know precisely both the velocity and position of a particle at the same time. So we know where electrons hang out most of the time. We can predict where they're at the majority of the time, but we cannot say for certain where a particular electron is at all of the time. So they do move around. They move around. However, we can predict a general location of where they're located the majority of the time. So this again goes along with this for probability of an electron to occupy a certain region around the nucleus. We don't know exactly, but we know where it's probably at. Now, this is just a diagram that shows you the quantum mechanical model of the atom before collision and after. Not really important for our full understanding of the atomic model. Another scientist that was important, it was Schrodinger, and he treated electrons as waves in a model known as the quantum mechanical model of the atom. And his equation was applied as well with other elements, not just hydrogen. Now, this is called the density map. What this is it's predicting where the electrons will be at any given time. So you can see on the density map that certain electrons are in here closer around the nucleus. This would be the nucleus of the atom. Some are further out here, some are further out here, and some are further out here. Now, remember, these atoms are three-dimensional. They're not flat. So it's difficult to represent what it actually looks like and where these orbitals are. But you have to picture atoms are spheres. So those electrons, even though they seem scattered all over the place, they are in a sphere, and those spheres appear to be overlapping because it's not just a flat surface with circles around it. Okay, so back to our principal quantum number n. This tells us the relative size and energy of atomic orbitals. And N specifies the atom's major energy levels, called the principal energy levels. So again, the one closest to the nucleus is energy level 1, then energy level 2 is a little further from the nucleus, energy level 3, and so on. So in this diagram here, you can picture the nucleus as being right here, okay, and then they're kind of showing you where the electrons would line up around the nucleus. So the higher the energy level, the further from the nucleus the electron is residing. Now, you guys are not going to be required to know the shapes of orbitals and predict this, but like I said before, atoms are three-dimensional. So the way their electrons occupy space around the atom is also three-dimensional. So the 1s orbit, the s orbits are spherical. They're round around the nucleus. Then we have p orbitals that are dumbbell shaped, and they're in three different planes around the surrounding the nucleus. And then we have d orbitals that are in a completely different plane than the p or the s orbitals. The reason the electrons line up this way is to minimize repulsion, because remember, electrons aren't attracted to each other, they're negatively charged. They are repelled by one another. So basically, they try to get as far away from each other as they can. And as a result of that, they take on these various shapes around the nucleus of the atom. All right, so these are hydrogen's first four principal energy levels. And it's showing you that when energy level is 1, we have an s orbital present, and we have one orbital relating to that and number of orbitals relating to the principal energy level. We'll go through this in more detail in the next section.